Welcome to the CropLogic final presentation. Over the past 10 weeks, our team has built an AI-powered farming intelligence platform. On the screen, you can see our MVP's geographic focus. Hungary, with several key sunflower and rapeseed fields identified. Our agenda today will cover the problem statement and our core objective. We'll then walk through the system architecture, covering the back-end, model, AI agent, and front-end. After a demo, we'll conclude with our achievements, limitations, and future work. The core problem we're addressing is the critical inefficiency in agricultural data management for small and medium-scale farmers. Currently, data is fragmented across many sources, and farmers lack integrated, user-friendly tools to interpret it. This gap delays decision-making and ultimately hinders profitability and economic growth. To scope this project, we started by asking key questions. We focused on Eastern Europe to support small-scale farmers, particularly beekeepers. This led us to Romania, Hungary, and Bulgaria. The plants we chose to track during the research phase, acacia, linden, rapeseed, and sunflower, are common in this region and are critical crops for supporting honey productions. This background research confirmed our choice. These maps show that Hungary has significant, widespread production of both sunflower and rapeseed, making it an ideal focus for our MVP. You can see the heavy concentration of sunflower production, 18%, right in the central region. The crop calendars also simplified our data modeling. Sunflower seed has a clear 8-month cycle, primarily between March and December, all within a single calendar year. Rapeseed, on the other hand, has a longer 13-month cycle that spans the winter. This helped us define our analysis windows, focusing on the key March to September growing season. Our high-level goal was to build a tool that could address 3 main areas: soil condition monitoring, honey harvesting readiness, and crop health monitoring. Given the 10-week sprint, we had to prioritize. We found the strongest data readiness for crop health, so we focused on delivering that as our minimum viable product, or MVP. So, the final MVP scope was clear. First, a geographic focus on Hungary, but narrowed to the Vas and Budapest regions to keep the data volume manageable and avoid out-of-memory errors during training. Second, we targeted sunflower and rapeseed crops. Third, we developed a crop health prediction model using a GRU architecture, which uses a 60-day look-back window to predict the next day's health. This is then accumulated into a 7-day forecast. Our deliverable is this functional prototype UI with a chatbot, all completed in 10 weeks. For data collection, our first challenge was identifying field geometries. Building our own computer vision model was out of scope for this sprint. Instead, we used the EU crop map dataset from the Joint Research Center. This provided us with pre-classified geometries and crop types for all of Hungary. The main caveat is this data is from 2022, so we are operating on the assumption that crop types in these fields haven't changed significantly since then. The core metric for crop health is NDVI, or Normalized Difference Vegetation Index. It's a value calculated from satellite imagery that quantifies general greenness. While the thresholds vary, we implemented a clear 5-point scale for the UI. Values above 0.60 are optimal, very healthy. 0.30 to 0.60 is good, moderate, and 0.10 to 0.30 is stressed, poor. Anything below 0.10 is considered critical or non-vegetation. These density plots show our training data for the Vas and Budapest regions from 2022 to 2025. The green curve represents the growing season, while the gray curve is the dormant season. You can clearly see in 2022, the growing season NDVI values were much higher and distinct from the dormant season. Interestingly, as we move toward 2025, those two distributions appear to get closer. Our crop health model was trained on 30 features engineered from 5 key datasets. We used EU crop map for the field geometries and crop labels. We pulled NDVI from Sentinel-2 satellite imagery, and we enriched this with environmental data from ERA5 land and SMAP for soil moisture, and OpenMeTEO for weather data. Here's a high-level overview of the system architecture. The backend, built on Fast API, handles all data ingestion and API requests. We used Poetry for package management, which was crucial for maintaining a stable dev environment. The data layer uses a local SQLite database for metadata, like field IDs, annotations, and assessments, while the heavy NDVI data is stored in efficient Parquet files. The AI layer uses a LangGraph orchestrator to generate insights. While we planned an OCI deployment, it was deferred due to VM availability, so the demo runs on a local Docker Compose setup. Zooming in on the backend, the big picture is simple. A user interacts with the React frontend, which sends requests to the backend API. The API, running in a Docker container, then uses 3 data sources to generate a JSON response. It reads pre-processed NDVI data from Parquet files, queries the local SQLite database for metadata, and loads the trained forecast model to run predictions. The backend is organized into 4 main blocks: the web endpoints, data engineering, the trained model, and the AI agent. The API exposes several key endpoints for the front end to use, including /fields to manage geometries, /ndvi to get time series data, /annotations for user notes, and /assessments and /chat for AI interactions. To move this from an MVP to a full production system, several improvements are needed. This includes building automatic ETL pipelines to pull live data into cloud storage, like S3. We'd also migrate from SQLite to a scalable PostgreSQL database with the PostGIS extension for better geospatial queries. Finally, we'd add security for user accounts and improve chatbot quality by integrating a searchable RAG knowledge base. The AI agent layer is designed as a LangGraph orchestrator. When a user query arrives, the context summarizer first gathers all NDVI and spatial features, a feature orchestrator, then aggregates this context, normalizes the schema, and builds a feature vector for the ML agent. The crop health model agent then predicts the health score and trend. For our MVP, this model agent is connected directly to the chatbot, allowing users to query it for forecasts. The model itself is a gated recurrent unit, or GRU, which we chose for being more efficient than a traditional LSTM. The model takes 60 days of multivariate data, including NDVI and weather, to predict the next day's mean NDVI value. It uses 3 stacked GRU layers, with batch normalization and dropout, to learn temporal patterns and prevent overfitting. While it handles time series data well, it is computationally heavy, taking several hours to train. This is the data pipeline we used for training the model. After loading and cleaning the 30 features, the most important step was the train/val/test split. To prevent data leakage, we split by fields, not by time. This means the model was trained on one set of fields and validated on a completely different set, ensuring it learns general patterns, not just the history of one specific field. This slide highlights our key challenge. We tested performance in 2 scenarios. In Set 2, the zero-shot performance during the stable, non-growing season in October, the model was extremely accurate, achieving an average MAE of just 0.04. However, in Set 1, during the highly variable growing season from May to September, the error rate jumped significantly, with an average MAE of 0.21. This shows that while the model works, its performance degrades with high NDVI variability, indicating a need for retraining on more seasonal data. This is the front-end architecture, built using React and Vite. It's a bit complex, but it shows how we manage state. We use React Context to create a global state for managing fields, time, and data caches. Key components like the map panel and sidebar panel consume this state. This allows components like the NDVI overlay on the map and the time series chart in the sidebar to react to the same data, ensuring they are always in sync. Next, we'll show a pre-recorded demo of the application running in our development environment. Let's begin by populating the map. We designed the Import Fields feature to be flexible. The modal accepts both raw GeoJSON text or direct file uploads. When a user uploads multiple files, the front end processes them in parallel batches. Once parsed, these geometries are synced to the backend, and the map automatically zooms to the relevant region in Hungary, ready for analysis. For ad hoc analysis, we included a rapid prototyping tool. Using the rectangle tool, a user can draw a bounding box on the map. The moment the mouse is released, the new field is committed to the central state and persisted in the database. Behind the scenes, a critical optimization happens here. As soon as a field is created, the client tessellates the geometry and sends this data to the back end. This breaks the polygon into a grid of cells at multiple resolutions, down to 10 meters. This pre-computation is what allows us to render complex overlays later without crashing the browser. We handle data loading in two ways. By default, it's dynamic. As you pan, the NDVI overlay component fetches only the geometry cells needed for your current viewport. However, for power users, we built the force load capability. This modal lets you select specific fields to pre-cache. It ensures that every grid cell geometry is loaded into browser memory immediately, preventing any visual stuttering during deep dive analyses. We apply that same caching logic to the satellite data itself. Using force load NDVI, we can fetch the entire time series of health values for our selected fields. While optional, this step can enhance the playback experience. It eliminates loading delays and enables perfectly smooth animation when scrubbing through the growing season. Preloading time series is time-intensive, so use it only if really needed. Clicking a field reveals the heart of the application, the Field Detail panel. This interactive D3 chart visualizes the NDVI trends over time. What's important here is the architecture. The chart, the time slider, and the map are all synchronized via a global time state hook. If you click a date on the graph, the map updates instantly, and if a specific day lacks satellite coverage, our system automatically displays the closest available date so the user never sees a blank map. The overlay uses a standard NDVI color scale, green for optimal health, fading to yellow for stress. We built this as a modular layer. This means future data sources, like soil moisture or honey harvest confidence, can plug directly into this same visualization engine without rewriting the front-end core. To capture ground truth, we implemented field annotations. Users can scroll down, select a specific health label, like pest or disease, and attach a photo directly from the field. These notes are saved to our SQLite backend and displayed in the log. For reporting, the export service aggregates all these notes into a CSV file. allowing farmers to easily share their findings with external stakeholders. For deeper insights, the Analyze Field button triggers our AI agent. This is an asynchronous backend process that compiles a comprehensive health report, including confidence scores and actionable recommendations. We also implemented a robust export feature. The reporting function generates a PDF and takes a live snapshot of the current map view, embedding it directly into the document. Finally, we have the integrated AI assistant. This isn't just a scripted bot. It connects to our LangGraph orchestrator to answer dynamic questions. Because the chat panel supports Markdown rendering, the assistant can return structured data, like formatted forecast tables or bulleted lists, making the information much easier for the user to digest. The most powerful feature of the chat is its context awareness. The component reads the currently selected field from our global context. So, when you ask for a 7-day forecast, the system automatically injects that specific field's ID into the payload. This routes the request to our GRU model, ensuring the prediction is generated specifically for the unique microclimate and history of that exact location. Here is the main field view. A farmer can compare their field's NDVI values against neighboring fields. This is a key feature, as it helps them benchmark their performance and understand if a problem is isolated to their field or is a wider regional issue, like weather. The AI assistant is fully integrated. Farmers can ask for a 7-day forecast for their selected field. The bot, which is connected to our GRU model, provides a full table of predicted NDVI values and health statuses, along with a human-readable summary, analysis, and recommendations. In addition to the chatbot, users can click the Analyze Field button to trigger the LangGraph orchestrator. This generates a complete AI field report. The report provides a snapshot of the field, core AI findings, a detailed explanation, and a confidence breakdown, all of which can be exported to a PDF for documentation. We also successfully implemented field annotations. Farmers can add notes, assign a health label like pest, and upload a ground truth photo. This data is saved to our SQLite backend, and all annotations for a field can be exported as a CSV file for external analysis. To expand beyond Hungary, several components are required. First, our front end needs to support drawing full polygons, not just rectangles. Second, the model agent must be retrained to generalize to new regions and crop types. Finally, for non-EU countries, we would need to build our own computer vision model to classify crop fields from satellite imagery, since we would no longer be able to rely on the EU crop map dataset. Enabling live data is very feasible. As this table shows, the ETL scripts to pull live data from our key sources, like OpenMedio, ERA, Fiveland, and SMAP, are already written and available in GitHub branches. The primary next step is to hook these scripts up to a production API endpoint and an automated data pipeline. To summarize, our key achievement is a working web app with 7-day forecasting for sunflowers in Hungary. Our main limitations are that the chatbot's conversational ability is limited, and the model agent is not yet fully connected to the main orchestrator flow future work we'll focus on enabling the live data APIs, integrating real-world sensors, and adding user authentication. This slide provides a brief overview of our Kanban status, showing the tasks we completed during our sprints versus those that were descoped or are still in planning. This project was a massive collaborative effort. I want to thank all the key contributors who worked on machine learning, back-end, and front-end development, as well as all the collaborators who assisted with data and AI modeling, and our project manager, Joseph. Thank you for your time. This is the end of the CropLogic presentation.